Welcome everybody to week 11 of the Math Club for Adults. And tonight we're going to talk about some number theory. And this will be a set of lessons that I'll teach that'll recur. But I wanted to start with the basics from the beginning to give everybody a chance to enjoy what is just an awfully large set of ideas that have one thing in common, that they deal with the integers. And so I'm going to start with kind of a presentation here before I get into divisibility, which is what I'm going to cover some tonight and again next week. But one of the things I think makes people feel a little bit intimidated is they don't really know where a course in number theory is going to go at the very beginning, right? And here I want to talk a little bit about the structure of an integer, and that we can view it in several different ways, and just recognizing that there are these multiple ways to view the structure of an integer certainly helps a lot of people get a sense of what it is we might be doing, or the kind of tool set we might be developing for elementary number theory. So here I've got this document here where I've written several different ways to view an integer, and the most common one, the one that we're taught from the very beginning, is to look at an integer in terms of its digits, each of which groups together, some powers of 10. And that's a way that we can keep track uniquely as we count through the integers. We can go back, we're doing this too, but we can keep track of them all uniquely that way, and then just express the digits one at a time without those powers of 10 being involved, because we know that as we write them in order, the powers of 10 decrease in that order. And we can do this in base 10. We can also, in our ordinary decimal system, we can also do this with other integers. Note that this is two different ways to express the very same integer. That quantity can be grouped in terms of sevens, and it can be grouped in terms of tens, and perhaps in a future lesson we'll walk through the basics of how we do that. But for tonight we're going to cover other stuff. So that's one way to think of an integer, is just in terms of its digits. How much is it? Another way to view an integer is in terms of its prime factorization. There's only one way to break an integer into primes that we multiply together. And next week we'll talk a little bit more about this one, but this is one more method. Then there's a remainder form. And I'm calling this remainder form. I'm making that up for my own purposes. Remainder form, there's something that we call the division algorithm or the division theorem. I prefer to call it the division theorem, that says that an integer is any integer is a multiple of any other integer plus a remainder, depending on how we define the remainder. And we'll get a little bit more specific about that. But so much of what we want to do in number theory, or what is convenient to do, revolves around divisibility, numbers that are multiple, integers that are multiples of other integers, and to have some sort of remainder that we can sort of split off in cases that are not ideal, to recognize that and to think about what we're learning as this sort of extra thing beyond what is convenient, and how to deal with that inconvenience, perhaps. That's one way we might be able to view handling the integers. And then there's algebraic expressions, and we're going to talk some about that tonight. We're going to talk about the first one, but algebraic expressions can mean anything, and we can get quite clever with them and involve all of our clever algebra. I just wanted to walk through, and most everyone has seen at least some of these, but may not have really thought about developing a toolkit for handling the integers in terms of these different forms and structures of integers. So then another thing, very often when I teach number theory, I talk a little bit about being investigative, because number theory, there's such a broad possibility of investigating. The problem solving is a lot of fun. A lot of recreational math revolves around it, but I just kind of listed here some of my favorite problem solving questions, and I might stop from time to time while we're working a question and ask these questions. What's interesting or useful? Sometimes I say useful, something with utility. What's ugly about this problem, or what is the obstacle? And what can we do to move forward? That's very often the decisive question. Is there something we can do? Yes, do that thing. It happens. And then what are the important definitions? And that's a question that that begins to get more interesting and deeper when we get into more serious mathematics. But a lot of times we're chasing definitions or really getting to the nitty-gritty of what we don't understand about a definition in order to be able to answer a question. So there we are. There's the beginning. And tonight we're going to talk about divisibility. And so I'm going to go ahead and just sort of at least give lip service to some basic theorems that involve divisibility. And I'm actually going to I'm going to open just to walk through and make sure that I don't skip one, a college textbook that I had on number theory. And I'm going to go ahead and say this about it. We've come a long way in terms of printing nice textbooks. This is from a mathematician named Landau, and it is an old book that if you're hunting for this book, you might have to pay a few $100s from a specialty book dealer or something like that. But when I look at this, I think, wow, we really do a better job of teaching now, and hopefully we can display some of that here. But what are some basic divisibility theorems? And right away we want to know things like, is divisibility transitive? And I'll go ahead and write some notation. A divides B, and we'll go ahead and say A and B are integers, are elements of the set Zahlen. Zahlen being the German word for integer. A and B are integers. A divides B, and that's equivalent to saying that B divided by A is also an integer. And then something that we may notice intuitively is that if we have a couple of divisibility statements, if A divides B and B divides C, okay, and I'll stop writing this at some point, but just go ahead and write it a few times. If A divides B and B divides C, does A divide C? And we might say, well, by definition, B array is an integer, and we can name that integer. Might call it quotient 1, and C divides B, and that's an integer that we'll call quotient 2, and then the product of these is C over A, which is quotient 1 times quotient 2, which tells us that yes, C is a multiple of A, and therefore A divides C. We'll go ahead and write it like that to make the theorem look as nice and compact as possible. A divides B and B divides C. We pass that along transitively. Okay, so that's some very basics, and I'll go through some of the basics, but some of them I'll probably move a little bit fast through and imply. But a lot of the proofs wind up looking relatively the same. If you get the hang of one or more of them, then you get the hang of a whole lot of them at once. Another thing that happens with divisibility, and this is one that's important because we're going to discuss an algorithm that uses it. Actually, we're going to discuss multiple things that use it. If we have A divides B and A divides C, then two things occur. A divides B plus C, and A divides B minus C. And this time I'm going to stop, and I'm going to put some numbers to this. I want this to be, I want everybody to absorb this as intuitively as possible. So let's say 12 divides 108. That's my A and my B. And 12 also divides 624. Actually, no, I'm going to swap the numbers just because I want to stay with the positive numbers, at least for the moment, positive integers. All right, so both these statements are true. And then, if we take a look at 624 plus 108, that's equal to 12 times 52 plus 12 times 9, and that's equal to 12 times 52 plus 9. And we can generalize that, just plug the variables back in, and we make this d times q1 plus q2 or something like that. And again, 624 minus 108 is going to be a multiple of 12. And we can do something similar there. And that's going to equal 12 times 52 minus 9. And so, one of the ways that I like to talk about this is maybe there are 12 M&Ms in one of those little tiny bags of M&Ms that people give out for Halloween, mini M&M bags. And 12 times 52 would be 52 of those bags, of those little mini bags. And if we add those mini bags up, any number of them, then we should still have a multiple of 12. And if we take some away, if we subtract some, we should still have a multiple of 12. And so it's kind of intuitive, works both ways. And this is one right here. I'm going to go ahead. We could, talk about a few more divisibility theorems, but this is a point at which we have enough to actually do something that is very important in number theory. We're going to talk about something called the Euclidean algorithm. But before we get into the Euclidean algorithm, let's just take a look at a question like, what are the divisors of 12? Actually, you know what? Let's do divisors of all three of these numbers, 12, 624, and 108. And 12 doesn't take too long. And even if we don't know any special methodology for doing this, we could eventually just hunt them down and write them all out. 624, this one's more complicated. Oh goodness, did I bite off a lot here? Let's see. I think we're gonna have 20 different divisors. Let's see, 1, 2, 3, 4, 6. What was it gonna be? Is 13. So 8, 12, 13, goodness, 16. Let's see, 1, 4, 8, 16, 3, 12, 24, 48, 13, 26, 52, 104, 208, and then 39, 78, 156, 312, and 624. I need to count these up. 8, 8, 4. Yeah, we have 20, so that's the right number. Okay. And then finally 108, where we have 1, 2, 3, 4, 6, 9, 12. Should have done this in a different order. It's going to be 12 of them total. 18 and 27, 54, 108, 36. Yeah, that's all of them. Okay, so we see all these divisors here. And we might ask a question like, what are the common divisors of two integers? We might want to know, when is it that we can divide them into the same number for any reason? There's all kinds of problems that we might ask at that point. But there are a number, and in fact, all of these are common divisors of these two integers. And they have no common divisors that are not divisors of 12. In other words, the set of divisors of 12 is exactly the set of common divisors of 624 and 108. Okay, well, that's an interesting observation. Is that something that we can generalize? Is that something that always takes place? Okay, first let's see if we can prove that all of the common divisors of 624 and 108 are divisors of 12, and maybe we could do that in a way that generalizes. So here we've got, I'll say this is A, and this is B, and this is C, and we can write B as A times Q1 and C as A times Q2. And if we say that D divides B and D divides C, D for divisor, then what is it that we know? We know that b over d, which is a q1 over d, is an integer. And we know that c over d, which is a q2 over d, is an integer. And that's 624 over the divisor and 108 over the divisor, what we're saying. That's an integer, and that is an integer for the purpose of this problem. So, okay, what happens when we add these together? Well, we add these together and we get b plus c. And if we divide this by d, then we're going to get aq1 plus aq2 over d. Okay, so what is it that we see and what is it that we can say? Oh, pardon. I just did that entirely backward. Not backward, but in the wrong order. We've got A over D times Q1 plus Q2. What does this expression demonstrate for us? Anybody want to take a shot? Well, in this expression, we know that this is an integer, right? We took these two integer expressions and we added them together, and we know that integers are closed under addition. If we add two integers, we always get an integer. And so we've added two integers together, and then we've substituted according to this expression of multiplicity of A. We've substituted, and then we rewrote things. We've rewritten things in this other form. And what we know is that if D is a divisor of A, then this thing is an integer. So if D is a divisor of A, then D divides B plus C. Is that fair? Can we go the other way? What would we do to establish that if D divides B plus C, that it must divide A? It's funny, a lot of times in areas of mathematics, going one direction with these types of proofs, you think differently than when you go the other direction. So it takes a moment to kind of clear your mind and look at it from the other direction. But John, you were about to say something?
I was about to say that in terms of the way that you set it up, I'm sorry, I was talking to Charlie. I'm assuming that A is defined as the greatest common divisor? Or am I jumping the gun on that?
So I didn't quite define it that way. I did pick it out that way.
Right. The point I was going to say is nothing in your algebra had any dependency. It seems like it could go the other way.
Okay. So in this particular case, yeah, if 12 is the greatest common divisor, if there is none greater, then perhaps we can go the other way. Is that what we want to do?
Yeah.
To now insert that condition. So how does that condition work for us?
What are you asking?
Well, you know that A over D is an element of Z. Right,
Yes.
if you just started and go in the reverse direction, so you've got two integers, you multiply them together, they're two integers, and then you can dissect them and proceed backwards from the arrow. The arrow's in the reverse direction.
Sorry, say again?
Right, so if A is the greatest common divisor and D is something that divides it, then I would just start at the very bottom of your proof. I'm multiplying two integers together. I've got and that is also integers. It's closed, so it's also an integer. The product is, and then you can expand out the algebra and dissect it.
Perhaps.
Wait. Never mind. Just B plus C doesn't necessarily mean the sum of B and C being a multiple of D doesn't tell me that the individuals are. I'm sorry.
So there's nothing that we've said so far that prevents, say, A over D from being exactly a half. And then if it is, whether you get an integer depends on whether Q1 plus Q2 is even or odd.
Right, but if A is the greatest common divisor, in saying GCD is 1 tells me that they're relatively prime.
Right. So we need an assumption like that Q1 plus Q2 can't be even. That is, it can't have 2 as a divisor.
Okay, so
Switches.
Right
we need
here.
some kind of greatest common divisor assumption to go the other way.
If the GCD of Q1 and Q2 is 1, then what does that allow us to say right here?
And A is divisible by D.
Then A is divisible by D. Yeah, in order for this to be an integer. Not necessarily. D could divide Q1 plus Q2. So do we need another theorem in there? Okay. Here's one thing that I like to do. Oh goodness, it's funny. I started teaching this, and I had in my head teaching the Euclidean algorithm, and so I feel like I fooled myself into thinking about two theorems here, or thinking about what I want to do with the Euclidean algorithm as opposed to starting this from scratch, and I apologize for that. Here's what I'm going to clear my head. I'm going to allow myself to clear my head and go ahead and start talking about the Euclidean algorithm, and I'm going to lay out the theorems, and I'll probably click my brain back into place when that happens. But you know, if we want to go through the process of finding, for instance, the greatest common divisor, which would mean finding all of the common divisors of B and C, then this is what we need to do. We want to know, we want to be able to trust two facts. One of those facts is that if there's a divisor of A and a divisor of B that are the same, we have a common divisor of A and B, then that common divisor divides their sum, and also we have a common divisor of A and B, then it divides their difference. And if we go both ways, addition and subtraction, then if we have three numbers, A, B, and A plus B, where A equals A plus B minus B, and B equals A plus B minus A. Any D that is a divisor of A and B is a divisor of A plus B. Any common divisor of A and A plus B must also be a divisor of B. Any divisor of B and A plus B must be a divisor of A. So any integer that is a divisor of two of these must be a divisor of all three at once. So, and an example of that would be if we have 12 M&Ms in a bag of 620 or 52 bags of M&Ms, 12 in each bag, or we could have 9 bags. And because 12 divides both of these things. 12 divides 732. There would be, sorry, 12 divides 700. There would be 700. If there were 732 M&Ms, we could divide them into bags of 12 at a time. And if there were 516 M&Ms, we could divide them into bags of 12 at a time. And this is going to be enough to allow us to start with two integers and have a computationally efficient algorithm for finding the GCD. And let's leave out the idea that this is the greatest common divisor for the moment. Let's just say that we're looking at two pairs of numbers, 624 and 108, and then 516 and 108. And what I declare is, or what I claim is that the common divisors of both of these two groups are the same common divisors. And I know this because 624 is 108 plus 516. And 516 is 624 minus 108. And so going either way, if you have a common divisor of these two numbers, it must be a common divisor of 516. That's our second theorem. And if we have a common divisor of 516 and 108, then we have a common divisor of their sum, which was our first. So all the common divisors are the same, so the greatest of those common divisors must also then be the same. And what we've done here is we basically replaced a pair of numbers that we're working with another pair, and we're getting closer to zero. We're always going to stay in non-negative territory, but we necessarily took a step closer to zero for the sum of those two. And if we're always taking a step closer to zero, then we're creating a simpler and simpler situation. And there are only finitely many times we can take that step before we're done. And we'll have all the same common divisors that we had before. This time, instead of subtracting 108, I'll subtract 84 from 108. The idea is that we're always subtracting the smaller of the pair of integers from the larger. And sometimes I like to stop here. If you're programming this algorithm into a computer, you may have it stop when one of these numbers becomes zero or something like that. But usually actually I stop when I can just tell what the answer is. And I think that's what most of us do once we've learned this algorithm. And we can see that the answer, it must be 12. We're talking about all the divisors of 12 basically at the end. Every integer is a divisor of 0. So we're just talking about 12 as the answer. And it's neat that after all these years, well over 2,000 years, making use of this algorithm, still nobody's come up with a more computationally efficient algorithm for performing this process. And so we still use it today. Or actually had a number theorist claim to me a few weeks ago that there was some sort of, way to make some slight improvement when dealing with very large numbers. And I don't know what they were referring to since I don't keep up with that level, but I think that this is basically it. If there's any kind of improvement, it's at a very, very slight level. So here we are, the Euclidean algorithm, and we can make this quicker. And earlier at the very beginning of class, other page, very beginning of class, I mentioned the division algorithm right here. And we can make use of that at this time because we don't necessarily have to walk through all of these steps of subtracting 108. subtracting 108, subtracting 108, subtracting 108, subtracting 108. We know that, and we'll talk about this next, we'll prove this in a future class, but we know that for every integer, that when we divide that integer by, let's say, 108, that there is a unique quotient, in this case, 5, and remainder, quotient remainder pair. And the remainder, that 84, must be at least 0 and less than 108, which is what we're dividing by. And this basically says, hey, we could just subtract out all 5 of those 108s all at once and just bring us to that point right there. And then do the same thing again. We can write 108 as 1 times 84 plus 24. And okay, well, that didn't shorten anything. 84 is equal to 3 times 24 plus 12. And so we kind of skip some steps and jump down to the next point right there. And then we can say 24 is 2 times 12 plus 0. And it's when we see that 0 pop up that we know we're at the very end. So yeah, that's the extended Euclidean algorithm. We might insert that into the title there. So let's take a look at this. Following the Euclidean algorithm actually sets us up for something else that we can talk about, and this is called Bezout's identity. And this is something where we get into what I would call the fun. We get into some problem solving and seeing how it is that building up our toolkit the way that we are can be helpful. And I hope I'm pronouncing that correctly. Pete, can you correct me if I'm outside of pronunciation bounds for some of these old mathematicians? Well, I know that there's an accent somewhere, but I think I'm saying this right, Bezout's identity. So if we were to kind of walk backward through the Euclidean algorithm, we can wind up building 624 in terms of, we can build 12 in terms of 624 and 108. And and we'll see why that's important as we go. But how do we build 12 from 624 and 108? And here's what I mean. And just to be clear, I mean is a linear combination. Let's say that we want to express 12 as some number of 624s, some integer a of 624s and some integer b, and they don't have to be necessarily have to be positive. And here's an example of why we might do that. Let's say that Johnny and I we're swapping goats and cows in order to settle some debt. Maybe I owe Johnny $12 or he owes me $12 or something like that, either one. And maybe cows cost $624. I know that's an old price. But let's say that cows cost $624 and goats cost $108. And we might ask how it is we might swap cows and goats, because maybe I only own cows and maybe he only owns goats. But he's going to give me some number of goats and I'm going to give him some number of cows, and that's going to settle the debt. So how is it that we get to $12? So that'll be the motivation here. Cows and goats. So I'm trying to leave this up. Let me grab one of my handy dandy tools here. So, if we start at the bottom, Well, we can see 24 in terms of 12s. And then we can write 84 in terms of 24s and 12s. Let's see, let's isolate the 84. 84 equals 1 times 624 minus 5 times 108. So 1 cow minus 5 goats is equal to $84. Okay, that's good. So we're kind of isolating the remainder when we do that. That was helpful. Okay, let's isolate the remainder again here. We know that $24 can be made from 1 goat minus $84, but we know what $84 was. $84 was 1 times, well, 1 cow minus 5 goats. And so where are we now? We're at 6 goats minus 1 cow. And let's check the arithmetic. 648 minus 624, okay. Still works, that's all fine, that's good. And we know that 12, we made 12. We isolate that, was some kind of a bundle of $84 minus 3 bundles of $24, but we can write both of these in terms of cows and goats. We've got 84 is 1 cow minus 5 goats. And then we've got 3 times 24 was 6 goats minus 1 cow. And so here we have a total of 2 cows. Now, is that right? No, sorry, 4 cows. Minus 5, minus 18, minus 23 goats. Wow, is that real? I feel like, 4 times 624 is 2496. And then 23 times 108. See, 2300 and then 180, 2484. And that is indeed 12. Okay, so what we found here is 4 times an integer minus 23. I'll call these x and y. 4 times an integer minus 23 times an integer, that equaled 12, where 12 is the GCD of x and y. So what statement might we be able to say overall?
Hey, Matthew, one quick question. That 4 into 624 and then 23 into 108, right? So is that the unique solution to this, or there are other solutions?
Can we write 24 as a linear combination of 624 and 108? We'll discuss that in just a moment. We're going to discuss that. It turns out that there are necessarily infinitely many. If there is one, there's infinitely many. But this is perhaps the simplest one. These numbers get called Bezout coefficients, if I remember that correctly. And we can get the Bezout coefficients by basically just backing out through the Euclidean algorithm, isolating the remainders one at a time and walking through whatever the linear combination turns out to be. But that's actually where we're going to go next. We're going to discuss, what would a complete set of solutions look like. So here we are. In general, we might say ax plus by equals d has solutions when or when do we know it has solutions? Let's start with that.
When D is a multiple of the GCD of A and B.
Okay, when D is a multiple of the GCD of A and B, then we necessarily have solutions?
Yes.
Okay, and so that's a claim. Let's box this for a moment. We'll come back. Very often this is what's referred to as Bezout's identity. Let's start with something simpler and kind of work at this from the other direction for a moment, though. Let's say that we've got ax plus by equals 1. Now let's ask the question, when does this have solutions? And maybe it's easier to answer the question first. When does it not have solutions?
A and B
for a particular x and y. Maybe I'll make sure that we're focusing on x and y are kind of the main players in this game here, we'll say.
For instance, if A and B are both even numbers, then we know that there's not a solution.
Okay, or if x and y are both even numbers.
No, I meant for any x and y, if A and B are even, then the set of x and y that satisfies that equation is null set.
Yeah. If we have some kind of divisor, if D divides A, then, and this is one of the simple divisibility theorems that we actually skipped over, but we can prove very easily. And if D divides B, then D divides by. And we know that if D is a divisor of two numbers, then it's a divisor of their sum. And so the left-hand side is ax plus by. That means that D divides 1. So it would be a contradiction to say that there was some number greater than 1 or some positive number greater than 1 that divided ax plus by. So yeah, this is not going to have solutions when we have some sort of GCD other than the unit. But let's see if we can prove that it will always necessarily have solutions. And one thing I would say is, well, essentially we've already done that. If we were to walk through the Euclidean algorithm, then if we have two numbers that are relatively prime, by definition, our last step is going to look like GCD of 1 and 0, or 0 and 1, or something like that in some order at the very end. And then we're gonna have that remainder of 1, and we're going to be able to walk back through the process backward in order to write 1 as a linear combination of those two numbers. And that's really what Bezout's identity is that process of walking back, at least once we've connected that process to the Euclidean algorithm. So there, if A and B are relatively prime, then we have at least one solution. And now I'm going to take a look at an example of this equation that's much simpler than the one that we've used. I probably should have started with one that was simpler anyway. I kind of did this a little bit off the cuff today. It's been a long time since I've taught these basic propositions of number theory, and I thought that I would snap through it without having to think too much, and I was going to focus on the problem solving side later on. But here we are. If we have 2x plus y equals 1, one relatively simple solution to this is -1, 1. Okay, and if we have one solution, how can we construct another solution from it?
Well, I would say that if you multiply y by x and you multiply x by y, and then turn one of them into subtraction, you get 0.
Yeah, and the way I sometimes say it is, hey, we want to make adjustments to x and y that are collectively 0. And so if we make x go 3 in one direction and y go 2 in the other direction, then we see that balances out. And if we added it to our current equation, we'd still have 2x plus x prime plus 3x, or plus 3y plus y prime equals 1 when we add them together. Pardon. And so in practice, that's going to look like this: minus 4 for x, and then 3 for y. That would be going down 3 and up 2, down 3 and up 2. And we can go the other direction: up 3, down 2, 4 minus 3 is 1, up 3, down 2. And these are the integers on that line. Lattice points on the line: 2x plus 3y is equal to 1. And so, okay, if we have one solution, we have infinitely many, because this is a process we can repeat infinitely many times. So if there's one solution, and we know there is, since 2 and 3 are relatively prime, there are infinitely many. So we know there are infinitely many solutions. So, and we can always multiply this by anything like 12, for instance. And if we were to have the equation 24x plus 36y, well, it couldn't equal 1 because 1 is not divisible by 12, which is a common divisor of the left-hand side. We need no common, well, we could start with this equation and just multiply it by 12. Now we have an equation in which there are the same solutions as the first one, and there are infinitely many of those solutions. So what we know is that we have infinitely many solutions to the equation ax plus by equals d, where the GCD of a and b is equal to d. And not only that, but hey, we have infinitely many solutions to 2x plus 3y equals 1. What about 2x plus 3y equals 2020? What's an easy way to say we know we have infinitely many solutions?
It seems like we just take our previous solution and multiply it by 2020.
Yeah. Take any previous solution, multiply it by 2020. And as an example, we have negative 2020, 2020, and that's a pretty easy one to plug in right there. So yeah, we can say that ax plus by equals d times any integer, or what is the simplest way that we could possibly write this? What would we want to do? Maybe we say this has no solutions when and has infinitely many solutions when.
When n is divisible by d?
Okay, if n is divisible by d, then we are going to have infinitely many solutions, because ax plus by equals d had infinitely many solutions. We can just multiply the whole equation by n over d to get there. When does it have no solutions?
It seems like any other case it doesn't.
If the GCD of A and B does not divide in, then the left-hand side will be a multiple of the GCD, and the right-hand side will not necessarily, so we'll never have any solutions. So, oh goodness, I hope this is presented well enough to be followable. Does everybody feel like we've done a good job of building intuition while laying this out fairly rigorously?
I think you did a pretty good job, and I really liked the introduction of it in terms of cows and goats, and not just because I'm a big fan of goats. but yeah, I liked it.
Good. This is a little bit different than usual because it's not the presentation that I imagined myself giving or had given before. So now let's take a look at some problems and see how this helps us with some harder problems. We could stick to chickens and goats, of course, but we've kind of seen that. I've got one that I looked at earlier, which is an interesting, challenging problem that gives us a sense of the power of this. Now, there are multiple ways to prove this, but I want us to specifically use Bezout's identity. Also, even though I haven't taught modular arithmetic yet during the math club, I'm going to go ahead and insert that as a basic tool in our toolbox, and we'll go back and we'll develop that some on a later date. Now, what's the first thing? Just let's look at this problem, and like I said, my investigative questions earlier, I'm a big fan of getting started with those. So if I said, what's interesting or useful, what might we point to?
The general algebraic factorization tricks of if you had a squared minus 1, you get a plus 1, a minus 1, a cubed minus 1 as an expression. You know that breaks into a minus 1 and then a squared plus a plus 1. And
Possibly.
any sort of...
I apologize. I didn't know you had more. Go ahead.
Oh no, and just in general, when you have like a to the 105th power minus 1, you know that you're going to be able to factor it in terms of a to the 15th minus 1, and then in terms of the sums of the powers of a to the 15th, and so on and so forth. And so, I mean, that seems like the intuition, what's being asked in this question.
So I understand why intuition draws us there. If you've done that much more algebra work, and we can take an algebraic approach to this, but taking a more grounded number theory path toward this is going to provide us with something that turns out to be simpler. But when I ask what's interesting or what's ugly, I look up and I see this. This seems to be both the interesting part and the ugly part sort of at the same time. And when I see that within an equation, that's where I might focus. And so if we're trying to connect this to, or if we're asking what can we connect this to, we might say, okay, well, we've got these integers m and n, and we know that mx, that there exist integers, x and y, in fact, infinitely many pairs, such that mx plus ny equals the GCD of m and n. So that gets us started along a certain avenue of thought. And thinking in terms of modular arithmetic now, we can rewrite what's going on here. Whatever this GCD is, maybe we call it D, and we say, well, a to the m minus 1 is 0 mod D, which is the same thing as saying a to the m is congruent to 1 mod D. And similarly, actually, I'll just go ahead and jump to it. Oops, eraser. A to the n is congruent to 1 mod D. Okay. Now, what can we do with this up here?
Substitute it?
Yeah, great. We can say a to the, I'll call it, oh no, a to the GCD m and n is equal to a to the mx plus ny for some integers x and y minus 1 and that right there is a to the mx times a to the ny minus 1. And we look over here, a to the mx and a to the ny. And we have, fortunately for us, we took a moment to write the basic facts of the problem down in a way that makes them easy to utilize now. We know that a to the mx is congruent to 1 to the x, which is just 1 modulo d. And similarly, a to the ny is 1 to the y, which is 1 modulo d. And we multiply that together and we have 1 times 1 minus 1. So this is 0 modulo d. And that's it, we're done. So yeah, this is something where if we were to try to work through an algebraic solution, and I'll go ahead and mention this, I think I saw this problem my freshman year in college, or maybe it was in high school, I'm not sure, either one, and I did go about an algebraic solution, and now I just want to go back and bang my head over that because it's not nearly as easy to craft such a solution. Any questions or thoughts about this one? Okay, let's take a look at one more. Got one more interesting, challenging problem. Oh, where'd it go? Always liked the intersection between combinatorics and number theory. I like the principle that if you can count it, then it's an integer. That pops up in some fun places from time to time. And again, if our eyes are drawn to what's interesting and most interesting and ugly at the same time about this expression, we should be drawn to the GCD and possibly be asking, what's something that we can do with this? And what can we do with it? Anybody want to throw in a suggestion here?
Well, I don't have a great suggestion, but my intuition would say write n and m as like the greatest common divisor times some q, qn and qm, and then go from there.
So rewrite m and n as like dq1 and dq2.
Yeah.
Q1 and q2 are relatively prime.
Yeah.
And I have to say, before I got familiar with Bezout's identity, that was the way that I would have wanted to begin with a problem like this.
Yeah, so I figured you were going in a different direction.
Right, yeah. This is something that it winds up simplifying the direction of our logic with problems like this once we get a grasp on what Bezout's identity does for us. But if we just do the exact same thing we did in the last problem and say, hey, look, there are integers a and b. There exist integers a and b such that am plus bn is equal to GCD of m and n. And so we're here. And this seems like it's a little bit of a weird expression, right? We've got 4 different variables, but fortunately, we're only trying to prove that this thing is an integer, and we have some advantages on our side already. I mean, bn over n is just b, right? We can break this into 2 pieces. We have am over n times n choose m, and then we have bn over n, which is just b, times n choose m. And this part's easy. If you can count it, it's an integer. N choose m is an integer, times b, by closure, still an integer. And so we're really focused now just on this part right here. And so, okay. Well, maybe it helps to write out what n choose m is. So let's take this aside separately. We have a times m over n times n factorial over m factorial. And oh, well, we get some canceling that occurs here. We have a times n minus 1 factorial over m minus 1 factorial. Oh, well, that's just a times m minus 1 choose n minus 1.
We get there, but I think you were missing an n minus m factorial.
You're
Oh,
missing
really?
n minus n minus m factorial in the denominator, right?
Right.
But that'll remain the same.
It's fine, and it converts back, and it all works out in the end. I was just pointing out the middle got a little off the rails for a second.
Oh, wait a minute. Yeah. Wait. I switched the variables. Is that what you're telling me?
No. If you go to the far left, you should have n factorial divided by m factorial times n minus m factorial.
Yeah, the definition of m choose m.
Of course. Yeah, pardon me.
But that term will remain the same anyway, so you'll be okay.
Yeah, I botched this twice.
Any sort of variable that any integer, it's just there's some integer m. He was saying that because m and n, these are the numbers we're starting with, and we wanted to prove that identity that this is an integer. And he's saying we prove this for all pairs of integers where n is bigger than m. It doesn't matter what they are, just pick 2 numbers. If n is 17 and n is 2, then if I do this expression, it's going to be an integer.
And maybe we should note n minus m is n minus 1 minus m minus 1.
Right.
Yeah. Thank you for that correction. Now that was awful on me because I do teach combinatorics a lot. Okay, and there we are. And that's clearly an integer because our combinations are integers. And ta-da. And so I hope that these last couple of problems here, goats and cows, I mean, that's some good value out of this. It's certainly a problem that comes up, linear combinations of integers, and we're thinking about where it is that we have divisors. But it's really nice to see that, hey, anytime we see a GCD in an expression like this, we might just ask ourselves, what is it? What advantage might we gain by just saying, hey, we can always look at this as a linear combination of the integers that we're taking the GCD of, and then problem solve. And this last problem, by the way, was on the 2000 Putnam exam, which is the big college proofwriting math competition, 6 hours, 12 problems, and they're all pretty hard. I know that when I was in college, the median score was still 0. I hear these days it's 1 out of 120 points. And so the students have improved these days to the point that they're getting 1 problem or more than half the time. At least that's what I heard. I don't know for sure. but these problems are pretty challenging. But really, like, this feels not that challenging. Looking back at it, it's just a little experience, and we can all raise our level of handling number theory divisibility problems like this. Any questions or thoughts about any of these?
Yeah, I got a question. So when I was Charlie's age, and I was thinking, I used to amuse myself by thinking about math. And so the way I thought about this problem was, let's take two numbers that are mutually prime. So you've already divided out the greatest common divisor.
Is this going to be a new problem or one of these that we've already done?
I think it's going to be what we've already done, but just my way of doing it as a 10-year-old. So if you take two numbers that are mutually prime, let's pick two numbers that maybe are consistent with dividing the ones we had previously by 12. But anyway, start with one of them and ask yourself, okay, what's the remainder I get when I try to divide it by the other one? Well, it might be the number itself. And then just keep taking multiples of that number and ask what the remainder is. And I think the way I used to think through this is that you need to get like different remainders, eventually. So you got 50, let me look at what you have there. You have 52 is 45 plus 7, which is...
Yeah, my original numbers, 624 was 12 times 52, and 108 was 12 times 9. So I brought those up in case that's what you were talking about.
Yeah, so I wanted to do 52 and 9, I think. Divide both of them by 12. So I've got 52 and I've got 9. So let me just start with one of them, like start with 52, and ask yourself, what's the remainder when you divide it by 9? Well, you get something. Now double it, go to 52 times 2 and ask what the remainder is when you divide by 9. You get something. Now triple it, ask what the remainder is, you get something. And when you cycle through all of the remainders, it's kind of easy to see that you're not going to get a remainder of 0 until you get to 52 times 9.
Right.
And that means that you have to cycle through all 9 numbers before you get, before you get back to 0. If you hit two numbers that are the same, get two remainders that are the same, well, then you've got a contradiction because they're not mutually prime anymore.
Mm-hmm.
So
and we're going to do this in probably, I think, my third number theory class. We're going to go through this uniqueness proof. But the funny thing is this is exactly the same exploration I went through right when I was Charlie's age. Is exactly what you're saying, going through and finding out that you go through these cycles, both addition and then some with multiplication, so long as you've got something relatively prime with modulus. And that was just exciting to find out. And so
I thought it was really cool when I was a kid.
Oh, absolutely, yeah. It's discovering modular arithmetic and beginnings of ring theory. So out of curiosity, can we apply this? Do you see a way to apply it to either of these problems?
Well, you can always get any remainder that you want to, if you've convinced yourself that you cycle through all the possible numbers, you can get whatever remainder you want. And so that's tantamount to proving the identity that mx plus ny is equal to some remainder.
Yeah,
which could be 1, but somewhere in there it has to be 1. So.
Yeah, I developed my intuition in a similar way, and I found, unfortunately, that when I got to writing all the basic proofs to establish number theory, I actually kind of had to rebuild the way that I thought about it, because I guess maybe putting it in terms of the structures of number theory, what we're talking about is structure 3 right here, and then now we're actually looking at structure 4, maybe even with some observations that combine it with structure 2 just a little bit. We're not really using prime factorization, but we're using some of the same type of math to build up the basic divisibility theorems. But yeah, 4 versus 3. And this is one of the things that makes number theory very rich, is even with these 4 very basic ways to view an integer, you do have to learn each one sort of as a separate line of thinking in order to add them all together to be a good explorer in number theory.
Yeah, and so the approach, it's the same as approach 4. It's like, if I take ax plus by, well, think of a and b as being the 52 and the 9, and then x and y can be, various integers. I can get any remainder that I want to. So any number can be expressed that way, which is kind of what we've been proving.
Yeah.
But, my little 10-year-old version of it is, at least I get all the numbers between 0 and 52, or between 0 and 9. I can go from there to get different numbers. And
so, Charlie, the moral of the story is play with remainders and see what happens. Some cool things are going to pop out. I'll go ahead and pull the plug here. Thanks everybody for joining me, and hope you had a little bit of fun. And I think next week I'm gonna go down a different route. I'm gonna go down some prime factorization, and sometime in the future I'll do a 3rd class where I begin where we establish the basics of modular arithmetic, and then walk through a few cool problems that solves for us. And then we'll have a pretty open playing field for anytime somebody wants to come and do something with number theory. All right, have a good night, everybody.
Thank you.
Matthew.
Good night.
Have a good
Thanks, Matthew.